Hello, everyone. Thank you for attending our Economic and Social Wellbeing workshop. In this workshop, we're going to split it up into three separate components, in which this first component is where we're going to be discussing the general context and background behind how some new tools that have been developed can be used to quantify surfaces for forces X. And in this first part, we're going to learn about the RMRS raster utility project and tools, get familiar with a delivered cost model, which is part of those tools, along with getting familiar with batch processing, which will facilitate a wide range of analyses, discuss various inputs and updating, and walk through a series of examples. The RMRS raster utility toolbar and project more generally is a project that I've been working on for the last 5 or 6 years, in which it's a .NET coding library to facilitate a wide range of spatial, machine learning, statistical, and tabular type of analyses, and to do it in a manner that is very efficient, quick, and easy to implement. How this relates to our economic and social well-being aspect of the Stanislaus Forest project. Specifically in this case, I'm going to walk through a demonstration where we're going to be talking about how do we define what's on the landscape, and then how to define how much it would cost to move across that landscape and deliver it to a given facility using batch processing and those tools. To help set the background here, what we're really talking about is what type of prescriptions can we implement on the landscape to bring it to a fire resilient condition, and how does that differ from what our current existing condition is, in which case today we have higher fuel loads. So how do we go about doing silvicultural treatments, prescriptions to reduce those fuel loads, and how do we plan for that within a GIS modeling environment? To begin with, what we really need to know is the condition of the landscape. And we have various data sets at our disposals that identify things like biomass, land cover type, and even some aspects of fuel. However, we don't have the information that's related to field plot information like basal area trees per acre, which we'd classically use for silvicultural treatments to get at different scenarios on the ground for growing trees and or fuels. And so what we're going to do for this first objective is combine some of our land fire data with our field plot data to come up with what's referred to as tree lists from imputed data sets, which will provide that plot specific information so we can make silvicultural treatments. Specifically, what we're going to do is convert that tree list into a series of raster surfaces that depict various needle leaf and broadleaf components of basal area, trees per acre, and tons of above ground biomass. And we're going to use those within a batch processing, function modeling, RMRS raster utility set of tools to define prescriptions that will bring the landscape to a desired condition that is more fire resilient. In this case, we're going to use a simplified example where we're going to look at all the areas that have more than 165 square feet of basal area, and we're going to thin those areas to 165 square feet, and we're going to estimate that there's 15% leakage in terms of tons. And by using those tools, we can define those types of areas that are depicted here in the middle and left portions of the slide. And now that we have a desired condition and we know what the existing condition is, we can also look at how much it would cost if there was any material on the landscape to move it to a conversion facility. And here again, we can do this within batch processing and these RMRS raster utilities tools. And the concept here is to quantify distances, or more specifically, distances to move material to American wood fiber that are along the road and off the road, and use an algorithm in which that we define the least cost path, or the shortest distance. In addition to those distances, or what will be converted into travel times, we can include other costs, such as operation costs. How much does it cost to fall a tree, or how much would it cost for to administer some prescribed burning, or other administrative type costs. And to facilitate this type of analysis, we're going to use the delivered cost tool, which takes a series of inputs such as a digital elevation model, speed units, a roads layer with a field that defines for each one of the segment the speed a truck can move down, the location of a facility, the dollar per hour to use a semi-truck in this case, or its machine rates, and what is its payload. And then in addition to those on-road costs, we're going to look at some off-road costs, such as how fast can a skidder move, what is the machine rate for that skidder, and barriers to that motion, in addition to various operation costs such as felling and or prescribed burning, and other administrative type costs. And we can store all that within a file geodatabase, or more recently, and I should have updated the label but have not, into a folder system. So in addition to those inputs, we can have a simplified version of this once we've created our travel time rasters through this modeling approach, in which we can then just specify an elevation model and various machine rates and dollars per hour. And the way this tool works is it uses a digital elevation model to calculate surface distance. In this case, we're using the National Elevation Dataset, but we could use our LiDAR dataset, such as our project, or any other elevational model. And quite specifically, what this focuses in on is on and off-road costs. What is the distance to move material off the road to the nearest road cell, and then along the road to the conversion facility, and the least cost path, meaning the least distance to move that material. As far as inputs for roads, in this example, we're using Tiger roads, and this is where from those roads we're going to calculate that distance along the road segments using that least cost path algorithm. Each one of these road segments have been attributed with a rate of travel for a log truck based off of the surface conditions. And given the semi-trucks and regulations, here's the payload we can define in terms of how much weight the truck can carry. In this case, in terms of bone-dry tons, because our estimate of forest condition is in bone-dry tons. And an assigned machine rate. How much does it cost per hour to run that truck? For off-road costs, in addition to having a road network or a speed network, more precisely, we also have off-road travel barriers. And in this case, we're going to use national hydrography data to identify perennial streams, intermittent streams we're not going to be concerned about, and water bodies that actually stop motion to move material from one location to a road. In addition, we're going to include interstates and highways as these barriers, meaning that we're not going to skid directly to an interstate or a highway. And from that digital elevation model and those barriers, what we're really calculating is surface distance and the least cost path to move material on the landscape around whatever barriers we've spatially defined to a road segment. In addition, we're calculating a speed, a constant speed in this case for a simple example, but we could spatially depict that, and we could do the same thing with the payloads. In this case, 4 tons of bone-dry mass that the skidder can move, and a machine rate of $85 per hour. And upon hitting the go button or the execute button within the tool then takes all those inputs and performs a whole series of calculations to get at how many hours or what's the travel time to move material from that location along the road segment and off the road segments, which we can then convert those times into dollars per ton based off of payloads and rates. In this case, we can look at it spatially at every 30 square meters. What is the cost to move material from that location to the American wood fiber conversion facility? Now that we got these two separate components, we have what's available on the landscape and how much of it we desire to remove to meet a certain condition, along with how much it would cost to move that material to any given to a facility. We can then combine these spatially using these batch processing tools and function modeling to get at what are those spatial supply curves. And in so doing, you can graphically depict, spatially depict at very fine resolutions what the actual dollar per ton estimate would be to move that material to that facility. And what we can see in these two upper depictions, we can look at how many total tons have to be removed to meet our desired condition. And of those total tons, how many of them correspond to the bole of the tree, given our 15% linkage, that would correspond to dimensional type lumber versus chips for some sort of bio pellet mill or something like that. And we can combine all that to get at what is the actual implementation cost, what's the dollar per ton to move said material. In addition, we can combine that with a stumpage price. What's the going rate for the trees out on the landscape? What's the delivered cost rate, or the gate dollar figure? I meant to say. In which case, we can then calculate based off of how much is being removed a revenue. We already have a cost, and we can combine those together to look at what is the income at every given cell for any location within the Stanislaus. Now, take a special note here. These blue lines represent the Stanislaus vegetative polygons. And what we can see is that the spatial detail of information that we have is quite fine scale. And so how do we bring that up to a coarser resolution? Or maybe how do we bring it up to the resolution of wildfire risk priorities? Here again, we can use these tools to summarize this raster data for any given polygon. And for example here, we can take all the huck pods that were defined previously and summarize that income and volume estimates to get at supply curves that represent how many dollars or how many tons, how many acres can be managed for a certain dollar per ton value. And with that, I'd like to say thank you and join me for our next component of our workshop.